In the last video, we had developed the work energy theorem and took a look at a few examples to see how it would be useful. Here we're going to go ahead and take a look at conservative forces with an eye to developing the concept of potential energy. Once potential energy is developed in future videos, we will be using that to come up with an even more spiffy version of the work energy theorem that will make many problems very straightforward to calculate. So to this end, let's start by defining what we mean by a conservative force. A conservative force means that for every possible pair of points, the work done by all possible paths, work done by a force along all possible paths connecting 2 points. And again, this can be any 2 points. Is the same. So say, we'll just say this is point A here. This is point B here. What we're saying is if the object actually displaces along this path, and we calculate, and it's feeling some force like so, the work done along this path here is the same as, say, maybe along this path here, where maybe the forces are acting out like so. And it isn't just for these two, it's for every conceivable path that could connect our points A and B. And then we have to also say, and for all possible pairs of points A and B. This seems like a horrendously daunting task, but there are times where we can show it. There is an equivalent definition. You can prove that these two statements are the same. So I'll just say or. The work done on all possible closed paths so these are paths that loop back in on each other, is 0. I'm not going to dwell too much on this one here. The first definition will be more useful for me here. But these two, you can show that if you choose one of these, you can show that the other one has to be true. So the first thing you can use this for is to show which forces are non-conservative. So for instance, friction as an example. To show that two forces are non-conservative, all you gotta do is find two paths where the work done is different. So let's say you're sliding your book along your table like so. Oops, sorry about that. So it's your physics book. Like so. All right. Now we can imagine two different paths. So let's go with the purple path here. This is where we just go in the straight line. So displacement, we'll say d sub h for horizontal. That'll make sense in a moment. And then let's pick a different path. Let's go with this pink path here, where we first displace down some distance d vertical, and then we displace across the same distance d horizontal, and then we displace back d vertical, like so. All right, well here, for any of these displacements, what we're always going to get is if the displacement, if the displacement, say, is going this way, the force of kinetic friction is going that way. So, for the work done along the purple path, the work done by kinetic friction will be equal to the force of kinetic friction times d horizontal times the cosine of the angle between the displacement and the friction, which is 180 degrees. That's 180, like that. Well, that's -1, so we get this minus f dh. Okay. Now let's do it for the pink path here. Now for the pink path, to figure this out, we're going to have to break it into 3 chunks. This will be chunk 1, chunk 2, chunk 3. So along the pink path, this will be equal to work done by kinetic friction along chunk 1, plus along chunk 2, plus along chunk 3. But it all works out to the same deal. The work done here, well, the force again opposes the motion. The displacement's down, the force is up. So the angle between them is 180. This is minus f d vertical. Here, this is exactly the same as that, so it's minus f d horizontal. Here, this is sliding up, but friction is pointing down, again, 180 degree angle, so minus f d vertical. So this is equal to minus f d horizontal minus 2f d vertical, which is equal to what we found in the purple part with this extra minus 2f d vertical. So what we get is that the work done between these 2 paths here is not equal. And if you can find that for any pair of paths, if you can just find a pair of paths where it's not equal, the force is non-conservative and you're done and over with it. So that's one good use of this definition, is if you can find a single counterexample where the work, if you can find a single case where the work done along 2 different paths is different, that's it, you're done and over with. The force is non-conservative, you don't need to consider anything else. To demonstrate that forces are conservative, that's a little trickier, but you can still do it by being a little clever about your math. So let's go take a look at a conservative force, gravity, and show that it is conservative. So here what we can imagine is we can take your physics book and we are going to let it end up down and to the right. Okay, so first we could imagine just plain taking the direct path here. All right, so if we go ahead and draw our diagram here, we'll see that the force of gravity, acts straight down, and our displacement is way over here, like that. All right, let's call this angle theta here. So again, the work done by gravity will be equal to the force of gravity times d times the cosine of that angle theta. Now this might seem a little ugly here, but if we look at it here for just a moment, we realize that this distance right here is my d cosine theta. But we can say this is my y initial, that's my y final. So my d cosine theta, y final, would be y initial minus y final, but because we want to write with delta y's, this is minus delta y. So we can make that substitution, say the work done is equal to the force of gravity times minus delta y. And then we can go ahead and make the substitution that the force of gravity is mg to get this minus mg delta y, or if you prefer, that's minus mg y final minus y initial. All right, so we proved it for the pink path. Let's do another path. Let's try the blue path here. Well, going along the blue path like this, we're first going to go in two segments here. So let's call this segment 1 and that segment 2. So here in blue, the work done by gravity will be equal to the work done in segment 1 plus the work done in segment 2. Now in segment 1, gravity is pointing straight down, but the displacement is straight to the right, angle of 90 degrees, and we've seen that forces that act perpendicular to the displacement do no work. So the work done along segment 1 is 0. So what about segment 2? Well, segment 2, that's just playing a straight line, right? So along segment 2, the force of gravity points straight down, and so does the displacement. So this will be equal to the force of gravity times that displacement, but we just showed that displacement is just this change in height here minus delta y. Fg times minus delta y. And again, same deal, we can put in mg to get minus mg delta y. Great, so it's the same for the pink path as the blue path. Now here comes the problem. We have to prove, it's not good enough to just say, yep, it works for two paths. You actually have to prove that it works for every conceivable path. To do that requires some math that gets a little sportier than what we would maybe like, but I can give you a flavor for how that would work. So just let me copy paste. Right here. Copy. Paste. Cool. Alrighty. And let me erase some stuff here that we don't need. Don't need that, or those, or that. Okay. There, we got everything. So now let's think about what would happen for just some absolutely arbitrary path, let's say in green here. Maybe, I don't know, this path right here, it's as good as any. The trick, and to do this rigorously mathematically is beyond the scope of this course, but the trick is you can't do it for the curved path per se, but what you can imagine doing is squaring out the path like this. So just doing a bunch of zigzags that are basically following, ooh, crap. So you can imagine squaring out the path like this. So basically just a bunch of zigzags that follow it. Now the idea is the work done along all of the horizontal zigzag parts of the zigzag, those are equal to 0. The work done along the vertical ones will be equal to minus mg times whatever the delta y is there. But now here's the deal. Any upward going pieces will be canceled by corresponding downward going pieces, because here delta y would be positive, corresponding delta y over here, that would be negative. The only uncanceled bit is, you guessed it, this bit right here, and so you end up with the work still being equal to minus mg delta y. Now you might say, hey, wait a minute, that seems kind of sketch. That doesn't look like the perfect path. And then here's where you have to invoke a little bit of math beyond what we're doing. The idea is that you make the zigzag path finer, make the zigzags less obvious, more frequent, less obvious. Then make them even more frequent, and then make them even more frequent. And then eventually the zigzags are smaller than the pixels that we're using to draw the image, to draw the curve. And at some point, it's indistinguishable from the actual path you were thinking about. Now, to prove rigorously mathematically that that's legit is beyond the scope of what we're doing here, but that's the flavor of how it works. So we get that the work done by gravity is equal to minus mg delta y. So now here, what's going to become useful for us is to define potential energy. And we will start, sorry about that, potential energy. And if we take and the idea here is that we will say that the change in the potential energy of a system is defined to be the negative of the work done by the conservative force that we're thinking about. So this C is for conservative. So this is a definition of potential energy. Loosely, what it means is the potential to do work. That's where the term potential is coming from. Now, you are free to choose the function. Now, for instance, one choice we could make for gravity would be mgy. Let's test to see that that works. The change in the gravitational potential energy would have to be equal to the negative of the work done by gravity. So this would be mg times y final minus mg times y initial. So that'd be minus a minus mg delta y. Cancel, cancel. This is mg delta y equals mg delta y. So that checks. That is a legit choice. Are there other choices? Absolutely. We could choose, for instance, not that anyone would actually do this, so don't make this choice for technical reasons, but it's valid. You could choose to instead let your gravitational potential energy be mg times y plus some value a that has, as long as it's got units of meters, or whatever distance units you're working in. That would also work if we take a look at the change in gravitational potential energy. Would that be equal to the negative of the work, which would be minus minus mg delta y, which is mg delta y. Well, let's check. So this would be mg y final plus a minus mg y initial plus a. So this would be mg y final plus mga minus mg y initial minus mga. Hey, those cancel. And this is m, and the left-hand side is also mg delta y. And so it's valid. Now, I said don't choose this, but we actually kind of do. The way we do this in practice is we say that you are free to choose where y equals 0. Now, once you've made that choice, you are stuck for the rest of the problem. But you are free to make that choice, and you're free to make it in a way that will make the arithmetic convenient for you. Now, there are other times where, although technically you're free, there are many choices of a potential energy function. It'll turn out that because calculus, there's only one choice that will make doing the calculus necessary to construct the function non-tedious. An example of that would be the force of a spring. So we'll say spring force. So here, let's say I've got a wall here, I've got a spring, it's attached to some mass, like so. If I pull on the spring to the right of the equilibrium position, so we'll say this is the equilibrium position that corresponds to the relaxed length of the spring. If I pull the object over to the right, the spring is going to pull to the left on it. And similarly, if I were to compress the spring would try to get longer, and so it would be to the right. The way we usually write this is we'll say the spring force is minus k times x, where we choose x equals, whoops, my bad, where we choose x equals 0 to be at the equilibrium position. And if it's stretched, we'll say that this corresponds to x positive. And if it's compressed, we'll say that corresponds to x negative. Some books don't get fussed about the minus sign and just tell you to stick the direction in by hand, so that minus sign doesn't always show up. But I kind of like it there. But in practice, when you actually use springs, usually you'll just let the free body diagram tell you the direction. You'll stick the minus sign in by hand. So I'll just put that in parentheses to remind us, because the idea is if x is positive, the force needs to be negative. If x is negative, the force needs to be positive. So mathematically, that minus sign needs to be there. Now you can work out what the potential energy function for spring is. It turns out spring forces are conservative. It's a similar argument to what we did for gravity, but a little more complicated, and it involves the methods of calculus. At the end of it, what you get is that it's 1/2 kx squared, where k is what we call the spring constant. It's in newtons per meter. So it's just saying how many newtons of force will it exert per meter of stretch. And it turns out here you're stuck. You have to put x equals 0 at the equilibrium position due to technical considerations of using the methods of calculus to obtain this result. So sometimes you're free to choose where your 0 coordinate is. For other forces, the details of the calculus and the derivation force us to make a particular choice. Anyway, this will give us more terms that we can put into our mechanical energy. So we can say that the energy is equal to kinetic plus potential, and we can do bookkeeping and start breaking it apart and say that would be kinetic plus gravitational potential energy plus spring potential energy, and we could have more. Alrighty, so in the next series of videos, we will take this definition of potential energy and we will use it to come up with a spiffier version of the work energy theorem that will make a lot of problems go very smoothly. Catch you on the flip side.